In example 9, we are given a simple supported beam as seen here. It is spanning 6 meter and it is carrying a dead load of 8 kilonewton per meter, which includes the self weight, and the live load of 8 kilonewton per meter as well. And we need to calculate instantaneous deflection. That means the deflection that happens immediately after the load is being applied. That is like a short-term deflection, delta S, we need to find out. And the characteristic compressive strength of concrete is 32 megapascal. Also, we are given that the short-term load factor is 0.7 and the long-term load factor is 0.4. Young's modulus of steel, as we know, is 200,000 megapascal. The cross-section of the beam is as seen here. The overall depth of the beam, big D, is 500 millimeter. The width of the beam is 300 millimeter. It has 3 N28 bar, so AST is 3 N28 bars, and the small d, or the effective depth of the beam, is 450 millimeter. So first question is to find instantaneous deflection in the beam, that is the short-term deflection, and the second part of the example question is to find the total deflection of the beam. That includes the creep and shrinkage factor as well, that is the delta total we have to find. And we have to verify that both instantaneous deflection and the total deflection are within the allowable limit. Now let's see how we proceed with this. Now in this example, we are given that the span of the beam is 6 meter. The effective span of the beam, L effective, is 6 meter. The area of steel is 3 N28 bars, which will come out to be 1847.2 millimeter square, and the dead load is 8 kilonewton per meter, and similarly the live load is also 8 kilonewton per meter. The short-term load factor, the long-term load factor is 0.4, and we are also given that the characteristic compressive strength of concrete is 32 megapascal. Young's modulus of concrete for 32 megapascal compressive strength can be found out from table 3.1.2, which comes out to be 30100 megapascal. Now that's coming from table 3.1.2. And the Young's modulus of steel, as we know, is 200,000 megapascal. So once we know the Young's modulus of steel and concrete, we can find the ratio N that we will use it later on. That ES over EC is 6.64. That is the ratio between the Young's modulus of steel and Young's modulus of concrete. Now first let's find the serviceability load. So to find the service load acting on the beam, first let's find the short one, that applies instantaneous, or for the short time only. So for the short term we use G plus sigma S cube. Now please remember here that for the serviceability limit state, we don't have to use the load combination 1.2Z plus 1.5 cube, because for that one is for the ultimate limit state only. We are considering the ultimate load scenario in that case, but this is before the yielding. This is for the serviceability limit state, and we don't have to consider that load combination here, but we are considering the short-term load factor, and we can just add up the live load and dead load here. So in this case, the short-term the dead load is 8, short-term load factor is 7, and the live load is 8 as well, so that comes to 13.6 kilonewton per meter. And for the long term, the dead load is same, it hasn't changed yet, but we have to consider the long term factor, and QL is same as well, and Q is same as well. So that comes to Now, for short-term deflection, we need to find the effective moment of inertia, that is I effective. To find the I effective, there are a few steps that you have to do. That means you have to find the neutral axis depth, then you have to find the crack moment of inertia, and few other parameters that you need to find the effective moment of inertia. So to find the effective moment of inertia, we are first finding the neutral axis depth. So this is the crack section for the reinforced concrete beam. The concrete in compression is still in elastic state, and the width of the concrete in compression is B. The neutral axis depth is X, so this is your neutral axis depth, and your effective depth for up to the center of the reinforcement is D. That means this one is D minus X. And to transform the steel into corresponding concrete area, we have to multiply with N, and the area of the steel is NAST. So with this, we can find the neutral axis for the crack concrete section in the inelastic condition. So let's find it out. So in that case, so now taking the area moment about neutral axis, B is the area of the concrete multiplied by from the centroid to the neutral axis, this is X by 2, should be equal to the moment of the area of the steel about the neutral axis as well, and the area of the steel corresponding to the area of concrete is NAST multiplied by the distance of the centroid of the steel from the neutral axis D minus X. So this is a quadratic equation, and we can solve it to find X. So now let's put B is 300 millimeter here, so it is X squared by 2, and we compute it as 6.64. Area of steel we computed as 1847.2. The effective depth we know is 450 minus X. Again, this is the quadratic equation in X. Now solving the quadratic equation, we can find X, or neutral axis depth, is 155.24 millimeter from the top. So once we find the neutral axis depth, we can proceed to find the crack moment of inertia. Now finding the crack moment of inertia, it is denoted by ICR, and you know that ICR, we are finding the moment of inertia about the neutral axis for the concrete part, and also the transformed steel area as well about the neutral axis. So first, the concrete part, for the rectangular section, the moment of inertia about its base is bx cubed over 3. So moment of inertia about the base here is bx cubed over 3, plus now the moment of inertia of the steel about its own axis is very small, so we can neglect that, but we still have to transform this moment of inertia to the neutral axis. That means AD squared, that means the area is NAST multiplied by the distance is D minus X whole square. So plugging in the values there, we know B is 300, X we have computed as 155.24 cube, .64 is your N. Tension reinforcement is 1847.2, and D is 450 minus X is 155.24 square. Now if you compute that, it will come out to So that's the moment of inertia for the crack section. And we are one step closer to find the effective moment of inertia here. So but to find the effective moment of inertia, we need further few parameters here. So let's find out what is the cracking moment. The cracking moment is the section modulus of the section multiplied by the flexural strength of the concrete. Now the flexural strength of the concrete F dash CT.F we know is 0.6 multiplied by square root of compressive strength, and we have the compressive strength as 32 megapascal, so it comes as 3.39 MPa. So plugging that value in there, so Z is the section modulus, that is 300, and it is on crack section so far. 500 square divided by 6. So the cracking moment comes out to be 42.37. So that's your cracking moment. Now next step is finding the maximum moment due to short-term loading. And we know that the short-term loading W short is 13.6 kilonewton meter. And we need to find out what is the maximum moment in the beam when this short-term loading is acting. So we know that the short-term loading is WL square by 8, so the span is 6 meter. So basically we are using the maximum moment is at the center, and it is WL square by 8, and W is 13.6 kilonewton per meter here, and the span is 6 meters, so that comes out to be 61.2 kilonewton meter. So that is your maximum moment in the beam at the midspan when the short-term loading is acting. One another parameter that we need is the gross moment of inertia for on-crack section, and the gross moment of inertia for the on-crack section is BD cubed by 12, considering the whole cross-sectional area, and your width of the beam is 300, overall depth is 500 cube divided by 12, and that comes out to be 3125. So now we have all the parameters to find our effective moment of inertia. So we know from clause 8.5.3.1 we can find the effective moment of inertia. So the equation is given is so in this equation, I crack is the moment of inertia for the crack section, I is the gross moment of inertia we have found out, MRCT.F is the cracking moment, M star S is the moment due to the short-term loading, maximum moment due to the short-term loading. So we have found out all of that, and just plug in the values to find your effective moment of inertia. So the effective moment of inertia comes out to be 1941.65 into 10 raised to the power 6 millimeter 4. Now we have to make sure that this is less than I effective maximum, and the I effective maximum we know that it is given by AST divided by BD. It depends on AST divided by BD. So the area of steel divided by BD, and if you compute AST over BD, it comes out to be 0.0137, and according to the clause here, this is greater than 0.005. Therefore, your I effective maximum according to the clause is equal to your gross moment of inertia, which is 3125 into 10 raised to the power 6 millimeter 4. So whatever the effective moment of inertia that you have computed shouldn't be greater than that one, and so it is less than I effective max, so that's okay. So that's the maximum effective moment of inertia that you can use, and it is of course coming less than maximum effective moment of inertia, so you can use I effective as. So now we have all the parameters to find our short-term deflection. Therefore, finding the short-term deflection in the beam. So the short-term deflection for a simply supported beam with uniformly distributed load is at the midspan, and from the elastic analysis we know that the maximum deflection delta is 5WL4 384 ECI effective. So this is from the elastic analysis. So using that one, so for the short-term loading, the deflection, maximum deflection at midspan is 5WS, because we are using the short-term loading for now, L4 Young's modulus of concrete, and effective moment of inertia that we just calculated, or I effective here. So the short-term loading is 13.6. The beam length is 6000 millimeter. Young's modulus of concrete is 30100, and effective moment of inertia we calculate as 1941.65 into 10 raised to the power 6. Now that gives us the short-term deflection in the beam as 3.93 millimeter. So this is your short-term deflection at the midspan of the beam. Now to find the long-term deflection, that's the second part of the question. So the long-term deflection delta long, or delta total, goes to the short-term deflection plus the creep and shrinkage factor multiplied by the short-term deflection due to the sustained loading. So delta S sustained means is a short-term deflection due to sustained or long-term loading. So that means that is corresponding to WL equals to 11.2. So the deflection corresponding to the long-term loading, that is 11.2 kilonewton meter, that we have to find out using the same equation that we use, but WL here, it is a deflection due to the long-term or sustained loading, so we are using WL here. So the long-term loading or sustained loading acting on the structure is 11.2, and rest everything is still the same. So delta S sustained comes out to be 3.23 millimeter. So this is the short-term deflection due to the sustained or long-term loading. Now the creep and shrinkage factor KCS is given by this equation. And should be greater than or equal to 0.8. That's also coming from clause. So in this case, in our beam, the area of compression reinforcement is 0, so there is no compression reinforcement, so this goes 0, so your KCS comes out as 2. So with that, you can find the long-term or the total deflection in the beam, delta S plus KCS into, this is, you calculate as 3.93 plus KCS is 2 and this is 3.23. Therefore the total deflection in the beam for the long term is 10.4 millimeter. Remember, the short term deflection was 3.93 millimeter. That was the instantaneous deflection that happened on a structure when the load just act on the beam. That's elastic deformation, so that's 3.93 millimeter. And the total deflection in the beam, considering the creep and shrinkage deflection as well, comes out to be 10.4 millimeter. Now we have to make sure that both of these deflections are within the maximum deflection allowed in the code. So the maximum deflection, that is delta max, for the simply supported beam is given as L over 250 from table 2.4.2. L is, in this case, is 6000 millimeter, and so the maximum deflection that comes out to be 24 millimeter. So maximum deflection allowed in the beam is 24 millimeter, whereas our total deflection is 10.4 millimeter and the short term deflection is only 3.93 millimeter. Therefore, so it satisfies the maximum deflection requirement for the beam. Both of the short-term and the long-term deflection satisfies the maximum deflection allowed in the beam.